Greetings, this is Rob, Chief Flight Instructor for VATSTAR.com, and in this lesson we're going to tie it all together. Now ordinarily this is where I would say that to keep the video at a reasonable length I'm going to go through it kind of quickly, but this lesson is going to be a bit more complex than the ones we've done up till now, so I'm going to take my time a little more for this one. Still, pause and rewind as you need to, and if you still have questions, my contact information will appear at the very end. As always, let's start with a few vocabulary words. Oscillation. This is motion in a back and forth wave-like pattern. Have you ever heard of an oscillating fan? Those are the ones that turn back and forth while they blow air. The pendulum on a clock oscillates. Boats in the water oscillate when waves cause them to rise and fall gently. G-forces. These are the combined forces of gravity and inertia that act upon the airplane and its occupants and other contents. And it's given as a multiple of the normal force of gravity. So if you're sitting in a chair in front of a computer in a stationary building right now, as I expect you probably are, you're feeling 1.0 Gs. At least, I hope you are. If you ride a roller coaster and you get to the bottom of a hill where the tracks start to slope back up, that downward inertia combined with the upward acceleration causes some additional force that might be a couple more Gs. They make you feel temporarily heavier than you are. 2 Gs means you're feeling twice as heavy as you normally do. And for a guy my size, that's kind of bad news. Finally, lateral. That means to the side. We usually use that when talking about lateral motion or lateral forces, and in fact later on we'll be talking about lateral g-forces due to inertia during turns. But I'm getting ahead of myself. So when we're learning to control a plane in the air, we're mostly talking about making it climb, descend, or change direction. And occasionally we need it to change speeds as well. There are 3 main topics we need to cover in order to learn how to turn. Now, you guys that fly mostly or exclusively in airliners or other highly automated aircraft, you need to think of this whole lesson in terms of how to fly without the autopilot and autothrottle, because with those things engaged, your airplane automatically does for you a lot of what follows. I assume that you're watching this video and trying to earn the VATSIM P2 rating because you want to know more about the basics of really handling an airplane, really being a pilot and understanding fundamental flight controls, and not just how to program an FMS and watch the computer do all the actual piloting. If you're not interested in those things, I strongly recommend that you shut the video off now and probably forget about the P2 rating as well, because you don't need it. If you are really here to learn something, keep watching, and hopefully you will. And also, hopefully, you'll be better virtual pilots by the end of it. But anyway, where was I? Oh yeah. First, we need to understand how our flight controls interact with one another. Now, when I say interact, we already talked about how they act, meaning how elevators control pitch, ailerons control roll, rudder controls yaw, and thrust and drag control speed. But now we need to talk about how they interact, because each action has side effects that you need to be aware of and ready to control for and counteract. We'll then look at how those interactions play out in the context of a coordinated turn, and what that means and how to achieve it. Third, we'll talk about the accepted standard rate of turn, meaning how broad or sharp a turn you should make and why and how to control it. Finally, we'll tie it all together and examine the performance of a proper turn start to finish. So first, how flight control and power adjustments interact with one another. The first topic to talk about is a key one, and that is that adjustments in pitch and adjustments in power will almost always be made together. If you adjust one without the other, you usually will not get the effect you're looking for. Let's start by looking at climbs. And we're going to contrast climbing a hill in a car with initiating a climb in an airplane. So up top here is our little car cruising along at 55 miles per hour, and we encounter a hill. As we start to climb the hill, if we don't add any more power, that is, if we don't press a little more on the accelerator as we start to climb, what's going to happen? We're going to lose a little speed, aren't we? We'll drop to, say, around 50 as we first get to the incline, then maybe to 45 as we start to go up a little steeper, and maybe settle in at around 40 as we really start to climb the hill. Now on the bottom we're flying along in our little airplane, and let's say we're cruising at 90 knots. Now we reach a point where we want to climb to a higher altitude, so we pitch up a little, and we start to climb. But again, if we don't add power, same thing is going to happen. We're going to lose a little speed. So now we're down to 80 knots. Now here's where the result starts to differ, because in your car you might have started to lose speed, but you are still going to climb at the angle of the hill. You don't have a choice. Your car's not going to sink into the pavement. But in the plane, well, that's a different story. I colored the lower part here a darker blue to represent the angle of the climb that we want to take. But unlike in the top example, this is all just air. So as the plane loses speed, what happens? It produces less lift. When it produces less lift, it doesn't climb as much. So now we're down to 70 knots, and we're still trying to pitch up the climb, but without adding power, all we're doing is increasing the angle of attack and reducing the speed. Now we're down to 60 knots, and we're barely climbing, if even at all at this point. Let's see what this looks like from the cockpit instead of in my stick figure drawings. We're cruising along here at 3,000 feet and 90 knots, and we're more or less nose level pitch-wise. Now, we want to climb to 4,000, so we pitch the nose up about 10 degrees, but we don't touch the throttle. You can see that I started to climb a little, initially at about 500 feet per minute, but it's already dropped off to about 300 feet per minute, and I've lost a lot of forward speed already. Airspeed's now about 80, still dropping, 75 now, and barely making 200 feet per minute in the climb. Still holding 10 degrees nose up and still losing airspeed. I am still climbing slightly, but not much. Now I've got the nose up to 15 degrees and the airspeed continues to drop to around 60 knots. I'm temporarily back up to a 300 foot per minute climb, but it's tapering off again. Nearly 2 minutes into this example, I've barely gained 400 feet and I've lost a third of my forward airspeed. The point is, when we want to climb, we need to accompany that increase in pitch with an increase in power. The same is true in reverse when we descend. If we pitch down without reducing power, we'll start descending, but we'll gain airspeed. We'll generate more lift, and we won't descend as much or as quickly as we want to. So initiating a descent means a reduction in pitch and a corresponding reduction in power. Remember, changes in pitch and power almost always go together. If you want to speed up, just like stepping on the gas in the car, you what? Increase thrust, right? Well, duh. But in an airplane, what else do you have to do? Remember, changes in pitch and power almost always go together. If you want to speed up without climbing, that increase in thrust needs to be met with a decrease in pitch. We actually saw a great example of this in the very first lesson. If you've watched this whole video series, you may remember. I started off level at 1,500 feet and barely more than 50 knots. As I added power, I was able to fly more and more nose down, but still maintain 1,500 feet. I was trading off more airspeed for less angle of attack to produce the same amount of lift. By the end of the example, I was cooking along at a good 115 knots and had to fly actually a little nose down even to avoid gaining any altitude. So once again, increase in airspeed means increase in power accompanied by a decrease in pitch. Slowing down means reducing power, but flying a little nose up to keep the plane in the air at the lower speed. Again, changes
in pitch and power always go together.
Okay, hint taken. Moving on. Next topic. If you've ever tried flying a single-engine propeller plane and it kept wanting to veer to the left, this next section will help you understand why. Because in single-engine props, a dramatic increase in power and also in pitch can have a side effect that bleeds over into the yaw axis, pushing it to the left. Why does this happen? There actually are 4 reasons. The first is torque. Torque is essentially a force that's applied in a twisting motion, like when you're trying to open a stuck bottle cap or turn a screwdriver to force a wood screw into a piece of wood. In an engine, though, that torque comes from the pistons spinning the crankshaft inside the crankcase. Do you ever notice how classic American muscle cars do this little sideways twitch when you rev the engine? That's the effect of the torque trying to spin the crankshaft one way, while that same equal and opposite force is trying to spin the engine and the rest of the car the other way. In many modern cars, the engines are mounted sideways so you don't get that torque effect. But in all the classic American muscle cars of the 1950s, 60s, and 70s, the engines are mounted so the crankshaft and pistons are lined up front to back. There's a great scene in the movie Back to the Future Part 2 where Biff is about to chase Marty into the River Road Tunnel and he guns this big black Ford a couple times and he gives that glorious sideways twitch. Isn't that fantastic? Here's an even crazier example. This is a modified stock drag racer, and the torque is so powerful that the whole car rides up off of one front wheel when it goes. Well, okay, that's torque. And the same thing is happening to some degree in your Cessna Skyhawk when you suddenly increase the power. The crankshaft and propeller are spinning around clockwise, but the force from that is trying to make the aircraft roll around counterclockwise, i.e. to the left. Next is the gyroscopic effect of the propeller. When you get it spinning at full speed, it's just like the gyroscopes inside your cockpit instruments. Those little spinning discs don't want to change direction. Well, neither does your propeller. So when you pitch the plane up, the propeller resists that change in pitch, and it gives a little push to the side in a 90-degree direction, and that nudges the nose a little to the left as well. Third is the issue of asymmetrical thrust. This is a side effect of the fact that the propeller spins upward on the left side and downward on the right. So the airstream coming past the fuselage being pushed by the propeller is also being pushed upward on the left side and downward on the right. That upward flow on the left hits the vertical tail fin in the back, and there you have yet another little push that pivots the nose over to the left. And last but not least is another odd effect of the asymmetry of the spinning propeller, and that's called P-factor. P-factor is something that happens mostly when the plane's moving along at a nose-high attitude, like a tail dragger moving along the runway, but it's also when any single-engine prop is flying at a high angle of attack. So when the propeller is spinning clockwise like this, and the nose is tilted up relative to the passing airstream, the angle of the propeller is tilted, so the bottom is a bit further forward than the top. That means that the downward moving blade on the right side of the plane is actually also moving slightly forward, and the upward moving blade on the left side of the plane is also moving slightly rearward. The blade on the right side is going through the forward airstream slightly faster, so it's producing slightly more thrust. The blade on the left side is going through the forward airstream a little slower, so it's producing a little less thrust. Now, yes, those differences are fairly minor, but they're enough to give the plane an ever so slight left-turning tendency at higher angles of attack. Now, I explained all that so you understand why it happens in case you've been frustrated by that before. But it's not super critical that you remember all those reasons. What do you need to know about the left-turning tendencies? Well, for one, they're mostly an issue confined to single-engine, prop-driven planes. They're not a significant factor in twins because the asymmetry isn't as severe with one engine on each side. They're also not a significant factor in turboprops and jets because the thrust isn't generated as much by the big, heavy spinning moving parts. Turbine fans are kind of lightweight, relatively speaking, but the thrust is mostly coming from the combustion of the compressed air blasting out of the hole in the back of the engine. The second thing you need to know is that it's mostly an issue during takeoffs. Why is that, you ask? Well, torque is a problem when you dramatically increase power. When do you do that? On takeoff. The gyro effect is mostly an issue when you increase pitch. When do you do that most dramatically? On takeoff. Asymmetrical thrust is most noticeable at full power. When are you at full power? On takeoff. And P-factor is most noticeable at a high angle of attack. When are you at a high angle of attack?
On takeoff.
Yep, you got it. The third thing you need to know is that you can reduce or disable these effects in your simulator. At least you can in Microsoft Flight Simulator and its derivatives. Can't speak definitively for any others, but I imagine you can in most, if not all. In Microsoft, the settings are right here. But why would you? Like I said before, if it's safe to assume you're watching this because you want to learn how to fly your simulator more realistically, then leave these settings up all the way and simply control for them with a little right aileron or right rudder when they're an issue, mostly during takeoffs and occasionally at other times when you're at a high angle of attack. Actually, let's look again at the clip from earlier in this video where we demonstrated the pitch up without power up. But this time, let's focus on the heading indicator. I strutted on a heading of 120 degrees. But you can see that when the angle of attack starts to get higher, the P-factor kicks in, and I started drifting off to the left a little. If you watch the yoke, you can actually see me correct a bit right to keep the wings level. There's a bit of a correction there. When I pitched up from 10 to 15 degrees, it got even worse. Now, here's a standard takeoff where I initially got caught out by it a little, but then I controlled for it. We're on runway 15, which here has a magnetic heading of 148. As soon as I get airborne, you can see the plane tries to veer left, but I'm already throwing a little correction via right aileron to get it quickly back onto the runway heading. Moving on, the next interaction I want to discuss is the yaw axis with the roll axis. If you were to turn a plane using just the rudder, it's not actually going to enter a flat turn with the wings remaining level. It's going to roll into the turn as well. If you yaw the plane nose left, it will roll to the left also. Why is that? Well, imagine a running track with the standard 8 lanes, and I'm sure you know that the path around the track in lane 1 is shorter than the path around the track in lane 8. Well, now imagine you're in an airplane making a left turn. As you turn, the left wingtip is actually taking a shorter path around the turn than the right wingtip. That means that the left wing is traveling slightly slower than the center of the plane, and the right wingtip is traveling slightly faster than the center of the plane. The left wing, going slightly slower, produces slightly less lift, so it flies lower. And the right wing, going slightly faster, produces slightly more lift and flies higher. The effect of those two things is that the plane rolls in the direction it's being pushed by the rudder. And you've actually seen this already if you watched our earlier videos in this series. In the lesson where we talked about what the flight controls do, we showed this clip of the plane turning by rudder alone. And while at the time we were focusing on the yaw effect, this time look closely at the wings. As the plane yaws left, the left wing lowers, and vice versa. So you can cause a plane to turn on the roll axis without even touching the ailerons. But we'll talk a bit later in this lesson about why we wouldn't want to turn the plane this way ordinarily. Okay, the next topic is how rolling the plane affects its movement on the yaw axis. Obviously, when you want to change heading, you want the plane to turn on the yaw axis. That's the whole point of performing a turn. But we'll get to that in just a minute. When you first initiate a turn by rolling to one side, there's a very brief effect called adverse yaw, which sends the plane turning ever so slightly in the opposite direction first. To see this in action, we're going to hop into a Piper Cub. The Piper Cub is a very lightweight airplane, so it tends to get tossed around pretty good by all these forces. So for starters, I'm going to get the tip of the antenna pointed at this little cloud here, and watch as I roll the plane to the right. The nose is moving to the left. Then it starts moving to the right, but by then, I'm rolling left to get back to wings level, and the plane is really turning right now. So that's adverse yaw. Rolling right causes the nose initially to yaw left, and vice versa. It's very easily counteracted. When you initiate a turn, you want to gently apply both rudder and aileron in the same direction. Now that's just at the initial outset. You'll then need to be doing something else with the rudder, but we'll get to that. Here's how that looks in the Cessna Skyhawk. We're pointed at this little space between these clouds. Now, my rudder pedals tend to stick a little bit coming out of center position, so this application isn't as smooth as I would like it to be. But you can see as I roll to the right, my nose starts pointing to the right as well. I've counteracted the adverse yaw, which I knew was going to be coming, by applying both aileron and rudder at the same time. Now, once you get past that initial adverse yaw, the yaw that we want to happen kicks in and the plane starts turning toward the lowered wing. Why does this happen? Well, the lift vector, which used to be pointed straight up, is now tilted, and it's pulling the plane to that side. But why does it turn on the yaw axis to point to that side? The vertical tail fin resists lateral movement. It wants to cut forward through the air. So there's a weather vane effect where that sideways air hits the tail fin, it pushes against it, which turns the nose toward the direction of that sideways flow. Now, another thing happens with a banked aircraft. Actually, two more things. One has to do with that tilted lift vector, but hold that thought. The other is that a plane should have a natural tendency when it's banked to roll itself back to wings level. I'm going to yank this plane into a bank with the ailerons, but now I'm going completely hands off. I'm going to time-lapse this a little bit because the effect is kind of gradual. But notice that the yoke is staying completely centered and the plane is rolling back to wings level all on its own. Now I'll roll it to the left, and again, time-lapsed, watch the plane roll on its own back to wings level. What's that mean, and why do I point it out? Well, it means that if you want to maintain a bank angle for a turn, you as the pilot need to keep putting in just a little bit of aileron to that side to keep the plane banked in that direction. When you get to within about 15 degrees of your new target heading, you want to start a nice gradual roll back toward wings level. You don't want to wait until you're almost at the new heading and then snap the plane back to level, and you don't want to overshoot the new heading and have to turn back toward it. So starting that rollout about 15 degrees before reaching it is a nice conservative reference point that allows for a comfortable and gentle return to level flight. Now, we said a moment ago that there's another side effect of being in a banked attitude, and that's because the lift force that the wings generate is no longer pointed straight up. Some of it is still holding the plane in the air, but some of it is now making the plane turn, just like we discussed. And going back to lesson 2, What happens when the weight exceeds the lift being generated to oppose it? The plane descends. Let's take another look at the clip where I demonstrated how the plane likes to roll back the wings level on its own, but this time focus on the altimeter and the vertical speed. See what happens when the plane enters that steep bank? I'm falling out of the sky. Compensating for this isn't hard, but it's one more thing you have to remember when flying your turn, and that is to add a little nose-up attitude to counteract the loss in upward pointing lift. Here's the same right turn from earlier, but watch the yoke this time. There's an ever so slight pullback there to add just a couple of degrees to the pitch throughout the turn. It doesn't have to be much, but just enough to keep the altimeter where you want it, which in this case is 1,500 feet. This next topic, turn coordination, is highly misunderstood among simulator pilots, and I'll talk about why that is in a second. For now, though, please pay attention. Turn coordination refers to the balance of inertial forces on the plane through the turn, and the main gauge we watch is the slip-skid indicator. Like we pointed out in Lesson 5, that's literally just a little marble in a curved track, and it shows which way the forces of gravity and inertia are pulling on the plane. Back in that lesson, I used this clip as an example. Notice that while we're on the ground and turning flat, turning left yields an inertial force that pulls us to the right, and vice versa, just like when we're in a car. Well, on the ground, that's fine. But when we turn a plane in the air, the idea is that the gravitational and inertial pull should always be straight down toward the bottom of the plane, even when the plane is banked. The pilot and passengers should feel a sensation of being pulled straight into their seats and not toward either side of the plane during a turn. Why is this important? It's not just for comfort. It means that the aircraft is not slipping or skidding through the turn, which means that the nose of the plane is pointed straight into the oncoming airstream. Think of a race car on a banked race course. You don't want it to be slipping toward the bottom, the low side of the turn, and you don't want it to be skidding toward the outside, the high side of the turn. You want it tracking straight through the turn, pointed in the direction it's traveling throughout it. Well, the same's true in an airplane, because when the airflow is coming at the plane from an angle, it hits the side of the fuselage, which causes massive amounts of drag, and it also means that the wings are not traveling symmetrically through the airstream. Now, this is a borrowed clip from the Aircraft Owners and Pilots Association, but watch as stunt pilot Bruce Williams demonstrates to flight instructor Rod Machado exactly what can happen when you allow the plane to skid uncoordinated through a turn.
And I'll show you what happens, the classic base to final, skidding turn. So we roll into this turn with like we're turning toward the runway. Yeah. Now we add a little too much left rudder, watch the nose accelerate ahead of the airplane, and when we start to spin. Wow. And that happens quick, and it does happen quick, and it'll happen quick in almost any airplane. You'd be surprised. Even in a docile 172, it can come
So keeping the turn coordinated means adjusting the rudder throughout the turn in order to keep the G-forces centered, the nose pointed straight into the turn, and the little marble in the middle of the slip skid indicator. And the easy way to remember which way to adjust is to step on the ball, meaning push on the rudder pedal corresponding with the side of the indicator that the marble is on. Watching the clip of me making the turn in the Skyhawk, you can see that the little marble stays relatively centered the entire time. There's a little tiny bob right there, but I adjusted with rudder to keep it centered. Now, everybody pay attention. If you've been zoning out a bit thus far, that's fine, but focus for just a minute. There's a huge misnomer in desktop flight simulation software that unfortunately causes a lot of confusion on this topic, and that is the auto coordination feature that we mentioned in Lesson 4. Microsoft Flight Simulator has a control option that they call auto coordination that manipulates the rudder and the ailerons at the same time. This is how that looks. I'm moving the yoke left and right, and notice how the rudder and ailerons are operating simultaneously. I don't really know whether X-Plane has the same thing, but I assume it has something similar. If you don't have USB rudder pedals and you don't have a joystick that has a twist axis, this is a way around that. However, that name, auto coordination, is very misleading. It coordinates the movement of the control surfaces, but it does not necessarily result in a coordinated turn in the manner we just described. In all actuality, it really helps more with the adverse yaw situation at the beginning of the turn, but not really with the coordination through the turn. So keep that in mind during your flying, and in particular, keep it in mind when it comes time to take the P2 written exam. Alright, we're almost done. Just one more major topic, standard turn rate. So, when you're flying along and you need to change heading, how do you decide how wide or sharp a turn you want to make? Well, particularly when you're flying under air traffic control, it's good to have a standard for that so they have some idea where on their scope you're going to end up when you finish the turn. To fly a standard rate turn, we're once again looking at the turn indicator, but this time we're looking at the top half of it. Some have this little tilting airplane in it, and some have a vertical stick that tilts from side to side. And, like we pointed out in Lesson 5, the gauge shows how quickly your heading is changing. Here's a replay of the clip from Lesson 5 where we demonstrate that while turning on the ground. My feeling is that the tilting airplane could easily be confused for a bank indicator, so I prefer the leaning stick one, but your airplane might have either kind. The goal for a standard turn is what they call a 2-minute turn. And now that's not 2 minutes for any heading change. That refers to it theoretically taking 2 minutes to go all the way around 360 degrees. It's a rate of 3 degrees per second, so a 90-degree turn should take 30 seconds, a 180 should take 1 minute, and so forth. Now, how steep a bank you need to make that rate happen depends on your forward airspeed. The faster you're going, the steeper you need to bank into the turn to get that standard rate of heading change. There's a rough rule of thumb that says you take the airspeed, drop off the 0 at the end, then add 5 to get the bank angle. At 100 knots, drop the 0, making 10, then add 5, making 15. You should bank to about 15 degrees. At 250 knots, drop the 0, making 25, then add 5, making 30. Bank to 30 degrees to turn at the standard rate. In commercial aviation, you really don't bank steeper than 30 degrees most of the time, so any faster and you're just going to end up making a more gradual turn. So let's watch this clip again of my turn in the Skyhawk. Forward speed here is about 100, so the target bank angle is about 15 degrees. Here are the bank angle marks on the attitude indicator, so halfway between the first and second mark is my goal. And you can see the little tilted airplane with the wingtip right on the mark for standard rate. You can adjust as needed if your rule of thumb didn't put you exactly on the mark. If you notice, I started the maneuver right around 15 seconds after the minute here on the clock, and it's a 90-degree turn, so it should take about 30 seconds. And here it is coming up on 45 after the minute, and I'm arriving at my target heading of 090. Don't worry, we're only going to watch that clip one more time. So now, let's tie it all together and make a comprehensive step-by-step for performing a standard rate coordinated turn. We're going to start off at a heading of 000, due north. Actually, side note, ATC will usually verbalize that as heading 360, but it's the same thing. So first, we figure out where we're turning to and how steep we should turn to get there. We're going to turn due east to 090, and at 100 knots, we know we should bank to about 15 degrees. We're going to roll gently into the turn, using both aileron and rudder as to counteract any adverse yaw. We're going to pitch up slightly as to avoid any loss in altitude, and watch our altimeter to see if we need to adjust. We'll watch the turn rate indicator and adjust the bank angle to maintain a standard turn rate. That will also have the effect of holding a little aileron into the bank to prevent the plane from rolling back to wings level before we intend to. We'll be watching the slip skid indicator and adjusting the rudder to center the ball. Finally, as we get within about 15 degrees of our new target heading, we'll start rolling back to level, gradually releasing any rudder and up elevator we added during the turn. So, here we go, one last time. We're at 1,500 feet, turning to 090, and at the speed we know we need to bank to about 15 degrees. Aileron and rudder together to start the roll. Watch the altimeter and vertical speed, and pull back just a touch to keep the altitude steady. Watch the turn rate. Looks like I need to go a little steeper here. I'm watching the ball too and adjusting the rudder to keep it centered. Now, halfway between the 6 and the E on the heading indicator, that's 15 degrees to go. Start rolling back out. Gently release the rudder and the elevator while I do. And there I am, heading 090 and still at 1,500 feet. So, finally, let's quickly summarize the key points. Most any change in control surface position or thrust will have side effects.
Changes in pitch and power always go together.
Single-engine prop planes tend to veer left when increasing pitch and power, particularly when
On takeoff.
When yawing to one side, a plane will tend to roll in that direction also. When rolling to one side, the plane will initially want to yaw in the opposite direction. A banked aircraft, in addition to turning toward the lowered wing on its own, will tend to lose altitude and tend to roll back to wings level. The pilot has to compensate for both. During a properly coordinated turn, there shouldn't be any lateral G-forces. This means the nose of the plane is pointed straight into the turn, not at an angle. If the slip skid indicator rolls out of place, step on the ball. And finally, the standard rate of turn is 3 degrees per second, also called a standard 2-minute turn. Got it? Good. If you have any questions, and this lesson was a monster, so I know you will have questions, leave them in the comments or shoot them over to me in an email to cfi@vatstar.com. We'll see you in the skies.